Good evening, ladies and gentlemen. My name is Paul Olomolai, and I'm the Pro Vice Chancellor and Executive Dean of the Faculty of Environment of Technology here at UWI. We want to give you a very hearty welcome to this very first of our new public lecture series, which is aimed at highlighting and generating discussions on the brightest research coming out of our faculty. Our faculty spans the broad environment and technology knowledge space, including architecture, construction, property, geography, computing, and engineering. Within this knowledge space are 8 leading research institutes and centers, one of which is the Bristol Robotics Laboratory, where the lecture tonight is stemming from. The laboratory is a joint research enterprise between ourselves and the University of Bristol and boasts of significant research findings spanning mechanical and biological robots. With robots now becoming realities, questions regarding our ethical engagement with them are being raised, and Professor Alan full-time Winfield. You can see FT there. It's not part-time. There's nothing part-time about it. Professor Alan full-time Winfield will be helping us to answer some of the questions tonight. Alan was one of the stars at this summer's Festival of Ideas here at Bristol. He was the 2010 winner of the prestigious Royal Academy of Engineering Award for Innovation, and currently the EPSRC Senior Media Fellow and the Director of UWI's Science Communication Unit. I proudly commend this erudite scholar, scientist, engineer, and father of many roboticists in our quest for advancing our knowledge ethically from the unknown to the known, or the known to the unknown. So, Alan, over to you.
Thank you very much. Thank you, Paul, for that really overwhelming introduction. I'm flattered. Good evening. I'm really delighted to be presenting this first lecture in the FET Environment and Technology Lecture Series, public lecture series. Now, I'll be talking about robot ethics, but I have to say right from the very outset that I'm not an ethicist. I'm an engineer. But I'm an engineer who worries about stuff. And especially, I think, the impact, the implications of technology. I'm really excited by robots and robotics, but I'm worried about robots too. So what I want to do this evening is not to offer you an academic, erudite, philosophical account of the deep ethical questions in robotics. I can't do that. I don't have the right background to do that. Instead, though, I'm going to offer you a personal view of what it is in robotics and about robotics that worries me. Now, I'm going to do this present this in 4 parts. So the first thing I'd like to do is to reflect on the fiction and the reality of robotics, but then really importantly, and as Paul kindly said, we have a great robotics lab here in Bristol, one we're very proud of, and I'm going to show you the reality, the state of the art in robotics, because we've got them here. I don't need to talk about robots from anywhere else in the world in order to be able to present the state of the art. I'm going to do that not only because I'm proud of the robots that we have here and the robotics we're doing, but because I think it's important for you to understand the reality of robotics before we can start thinking about the ethical issues. And in the fourth part, the final part of the arc of the talk, I'll present, as I mentioned, my kind of personal worries about robotics and concerns about how to be an ethical roboticist. Now, if I were to ask you to think of a robot, most of you would say, okay. Now, that's interesting, isn't it? Very few people who perhaps have had no contact with robotics would have difficulty saying, okay, yes, I can think of a robot. And I'd reckon that most people would think of one of these. It's a fact, isn't it? Robotics have an extraordinary grip on our cultural imagination. Actually, it's not surprising, is it? The very word robot was first coined in a play, in a work of fiction. Robotics has been developed in our fictional imagination through science fiction and the movies. So most people, when you say think of a robot, they'll think of R2-D2 or Wall-E or Terminator. But then when you say, well, actually, the real world of robotics is this, then people go, oh, yeah, that's true. Yes, 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 I've seen some of those robots. So the reality of robotics is not only profoundly different to the fiction, but also rather dull. So, you know, we have robots that make cars and washing machines, like this guy here. Robots that collect your stuff from the warehouse when you order something from Amazon. Robots that operate on your prostate, if you're a man and unlucky enough to have an operation. The point I'm making is that robotics is an extraordinarily successful technology, but it's not at all like how most people imagine robotics and robots to be. There are some extraordinarily breathtaking robots in the world, in fact, off-world. This guy here, it's either Spirit or Opportunity, I'm not sure which, one of the Mars rovers. So robots have been exploring Mars for some decades. But as I said before, these robots are dull. Mind you, I'd rather have a dull robot, frankly, operating on my prostate. Thank you very much. I don't really want an exciting robot. In fact, I'd like robots to be about as exciting as air traffic controllers. That's a good place to be. Let me just reflect on the key differences between the fantasy of robotics and the reality. Well, these robots are, with two exceptions, humanoid. The only humanoid robot here, this guy in the top right, Robo Sapiens, is a toy. These robots are all pretty smart. Fictionally, of course, smart. They have artificial intelligence, in fact, very high levels of AI. They have personality. They have characters. These robots don't. In fact, the level of intelligence of these robots, the real-world robots, is very low, extremely low. Real robots are nothing like as smart as the ones that we fantasize about in science fiction. Now, I've painted a picture of robots being dull but worthy, but actually, the state of the art in robotics, the real state of the art, as I'm going to show you now, is extraordinarily interesting and very, very different to robots from the movies, to the fantasy. And I'm going to show you some of those robots now. So, in so doing, in presenting, if you like, the true state of the art, give you a little bit of a glimpse of the kind of robots that we might expect to see in the near future. The robots, as I mentioned, are all robots from the lab, and I just wanted to take a very brief moment to mention the history of the lab, founded in 1993, originally called the Intelligent Autonomous Systems Lab. You can still find old web pages out there for the IAS lab. And since 2005, the lab has been a joint research lab of UWE and the University of Bristol. It's the largest robotics lab in the UK. We have, it's probably more, Chris will correct me if I'm wrong, but around 50 at least staff and students. He's nodding. That's a big lab. And we have three main areas, and apologies for the misclassification, but you could roughly talk about biological robotics, human-robot interaction, humanoid robotics, and my own personal area of work, which is swarm robotics. I'm going to start by showing you one of my favorite robots. This is Scratchbot. Now, if we want to make robots that can, for instance, do search and rescue, imagine a collapsed building, and we need a robot that can search the confined spaces, the left when the building collapses. Conventional robot sensors are useless. Typically, those confined spaces in collapsed buildings are full of dust and smoke and debris in the air that mean that you cannot normally use cameras, conventional sensors. Now, the rat, the humble rat, wonderful animal, sees very well in the dark. In fact, it sees in 3 dimensions. It sees shapes and textures. You may not be aware of this, but the rat actually whisks its whiskers. It moves its whiskers backwards and forwards and feels its environment. So, colleagues in the lab thought whiskers would be a really amazing new kind of sensor for robots. And let me play that movie again, because you perhaps might have missed it. You can see that the large whiskers on the left and right-hand side of the robot's snout are whisking backwards and forwards. And when they find an object, then the robot reorients its face, its snout, to touch the object with its microvibrissae, the very small whiskers at the front of its snout. So what we have here is a remarkable engineering prototype of some very powerful new robot senses, whisking senses. And this technology has been taken forward, so we now in the lab have all kinds of different robots with little whisking things on the front of them. There's something else I want to mention about Scratchbot, which I think is particularly interesting, and that is that the robot has not just artificial whiskers, but has an electronic model of a small part of the rat's brain. So it processes some of the data from the whiskers using a kind of model of a little bit of the neural circuitry, the brain of the rat. It's very, very interesting. It's particularly exciting because it's a robot that is both a great piece of engineering, but also a scientific model for trying to understand a little piece of how the rat's brain works. It's a collaboration, in fact, with rat neurobiologists. And that is an interesting characterization because almost all of the work of the lab is collaborative across multiple disciplines. In this particular case, the rat folks are in University of Sheffield. I now want to show you another extremely interesting project. In fact, this is just the latest in a long line of robots that have been developed in the lab. Robots that eat food. Now, you may think, well, why do we need to build robots that eat food? Well, when we talk about robot autonomy, robots that can work on their own, we normally mean intelligence. We mean kind of computational autonomy, robots that can figure out what to do next on their own. The problem is, what's the point of having a smart robot if its battery runs out? Clearly, it's useless. Robots will need to be able to extract energy from their environment. There are all kinds of real-world applications of robots that we can envisage where robots will need to get energy from their environment. Imagine robots in farming, in horticulture, in agriculture, in forestry, robots doing environmental monitoring and so on. You might say, well, why don't we use solar panels so that the robot gets energy from the sun? But actually, it's not a reliable enough form of energy on its own. Let me tell you a little bit about Ecobot III. I mentioned that it's the latest in a long series of amazing robots, and I invite you to go and Google Ecobot and see the whole story. But Ecobot III is remarkable because it's almost certainly the world's first robot to have a complete artificial digestive system. And I really do mean complete. The robot works with a whole series of, now these kind of brick-colored things here, each one of those is a microbial fuel cell. It's a battery, except that it runs on food rather than chemical energy like conventional batteries. Now this rather complicated looking contraption, incidentally most of which is printed rather than machined out of metal, so we print our robots using rapid prototyping printers. But this machine lives in a box, in a sealed compartment. It runs on rails along the bottom, and it catches flies. Why flies, you might ask? Well, flies, it turns out, in fact, Yanis, who's sitting over there, is the very researcher who went through the tedious process of feeding the microbial fuel cells with all kinds of different foodstuffs and discovered that flies, or more particularly the chitin, the exoskeletal material of flies, gives the best energy conversion efficiency. And, well, they were lying around on windowsills, and they could be dried out. That was okay because it was the dry stuff is what the robot needs. But here, this is the first attempt to build a robot that catches its food as well as digests it, and it's rather like a pitcher plant in the sense that the robot has a device at the top that traps real living flies, They then fall into a kind of pre-digester, and then the kind of fly soup, if you can call it that, gets piped down into these two rings of little stomachs. It's like having 48 tiny stomachs. I'm looking at Yanis in case I'm getting it wrong. And it's those little microbial fuel cells that generate the electrical energy to power the robot. The robot has no other source of energy, yet has been demonstrated in the lab operating entirely from energy generated from these flies. Quite remarkable. I'd like to have a robot in my garden, for instance, that does the weeding. It's smart enough to know which are the weeds and which are the pests, and it eats them. Not the plants that I want to really grow, but the weeds. And it excretes fertilizer, perfect, and lives in the garden. It would be a kind of artificial hedgehog. That would be great, wouldn't it? Well, it's this kind of technology that will lead to those kinds of robots. I want to turn to one of my particular areas, areas of special interest, which is swarm robotics. So now for something completely different. This is a project called Cimbri. It's a European Union funded project. And let me explain that this little movie that you're seeing here is not real, or at least not yet. So the idea of the Cimbrian project is that we're building a whole swarm of little robots that are autonomous and mobile. They can explore their environment, they can sense each other, they can communicate, they can operate like a swarm of insects. But if the robots come across an obstacle, something that means that they cannot overcome the obstacle on their own, then they will self-assemble into a kind of three-dimensional artificial organism. If the robots then need to go back to being a swarm, they can disassemble. So it's a bit like Transformers, except that the robots are transforming from swarm to organism. Now, again, this is a collaboration between biologists and roboticists. And we're interested not only in the engineering applications of this kind of technology, but also the question of how, for instance, we can evolve using artificial evolution the strategies so that the shape of the organism that is generated is not a shape that we've predetermined. It's a shape that is automatically evolved by the robots themselves. We also are interested in biological processes, for instance, of homeostasis. That means we want the robots to be able to balance their internal energy resources. So, for instance, if this robot has formed this four-legged creature, then obviously the robots at the corners, the knees, if you like, will need more energy than the robots in the legs. They're pretty passive. So the robots will be able to share energy between the individual cells. Think of the robots as kind of cells in the organism. Our organism will also have an autoimmune system, so that if there are failures or faults within the organism, it will be able to repair those faults. So that was what we're going to do. What have we actually done so far? Now, bearing in mind that we're only around halfway through the project, so here are some videos of where we've got to so far. The one that I'm most proud of is the one on the bottom right, and this is my colleague Dr. Wengu Liu, who just about 2 months ago got this first demonstration working of two real robots docking, joining automatically, and the big guy that we call an active wheel is now hinging up, lifting the little guy off the floor, and they've now formed a very simple two-celled, three-dimensional artificial organism. In fact, this is the first demonstration in the project of that autonomous transformation, what we call autonomous morphogenesis from swarm to organism. Really exciting stuff. The problem is we can't do that yet for real, so we can only do that kind of thing in computer simulation. And I don't believe computer simulation. I won't believe it until it's actually working for real. I now want to turn to perhaps the biggest area of work in the lab, which is in human-robot interaction and humanoid robotics. And this I regard as an incredibly important project. Project called CHRIS, Cooperative Human-Robot Interaction Systems. Now, let me try and paint a picture for you about why this is important. Imagine that you're working, for instance, on your car. You're working on the engine or something, and you have a robot workmate, a robot helper. So you're working on the engine, and you realize that you need a spanner. And you put your hand out, and you say to your robot helper, "Could I have the 13mm spanner, please?" Okay. Now, the robot needs to know, firstly, what you mean by, "Could I have the 13mm spanner?" Actually, that's not too difficult in technical terms. What's far more difficult is that it needs to know what you mean by putting your hand out. Because remember, I didn't say, "And would you please place it into my hand?" So there is gestural communication. And really importantly, of course, the robot then needs to be able to select the spanner from its toolbox and put it into your hand without breaking your hand. That's really tough. Imagine that you finished using the spanner. The natural thing to do would be simply to hold your arm out. You don't even need to say anything, because a human workmate would know what you mean by that. Well, the objective of this project is to research the technologies, the very difficult technologies that are needed for that kind of gestural communication between humans and robots. They don't have to be humanoid robots, but it helps, because clearly, you know, if you have a robot that's going to use tools like a spanner, then it would be useful if it has hand or limbs or something that approximate to human or humanoid limbs. Here are some of the robots that are being used in this particular project. Some of them look pretty weird, I have to say, but I really want to showcase this robot, Bert or Bertie, and in particular the fact that this robot was designed in collaboration with, but manufactured and supplied by a Bristol-based company called Elumotion Limited. Terrific company that I commend to you. And now a long-term partner, I would say, of the lab. Now, Bert has a kind of cartoon face. And I just want to show you one of the many sub-projects within the overall CHRIS project. This is the problem of shared attention. Now, when two humans look at each other, subliminally, we will move our eyes to point at an object if we're talking about it. So if you say, "Can you pick up the book?" then you'll look at the book on the table beside you. And again, subconsciously, the person you're talking to will see where your eyes are looking. And by that mechanism, you'll establish a shared attention to an object between you. Now, in this work, the robot up here and the human who is looking, imagine that you're looking at that robot, which is exactly what Alex, where's Alex, was doing, Alex over there. Alex is looking at one of these little post-it notes, that's correct, isn't it, Alex? And the robot has to figure out where Alex is looking and look at the same post-it note and establish a kind of shared attention, in this case through gaze. What we're not showing you here is the gesture as well. Now, what I want you the message, if you like, that I'd like you to get from this last little segment, this humanoid, human-robot interaction work, is that safe and effective human-robot interaction requires the solution of not one, but many very difficult problems. Very difficult problems. So the idea that human-robot interaction is something that the problem that's already been solved is simply not true. We can't yet do safe, effective human-robot interaction. And when each of the individual problems has been solved, you then have to put them all together and make them safe. And the, again, dull but incredibly important work of how to prove the safety of that human-robot interaction is another part of this very large program of work. I hope that what I've done there is given you just a glimpse. I mean, I can't do it justice. There's too much work, too much great work in the lab to show you everything. So I've just shown you a glimpse of the work of the lab, but I hope what I've done is that I've demonstrated that the state of the art is very different to robots in fiction and the movies, but actually more exciting, more interesting. But what does it mean? Well, one of the things that you might have picked up in the last few slides, the work I was showing you of the lab, is that none of those robots were particularly intelligent. Now, it's very difficult to determine exactly how intelligent a robot is. When I give talks, I'm often asked, well, how intelligent are intelligent robots? It's a hard question to answer. I mean, the simple answer is not very. But what people really mean, of course, when they say how intelligent are intelligent robots is, and should we be worried? The answer is no, but maybe yes. Maybe yes. There is a problem, and the problem, the first of the three ethical worries that I have, and I'm not pretending to speak for any other roboticist, but the first of the three ethical worries I have is what I call the ethical problem of not robot intelligence, but robot stupidity. The problem is that a lot of the robots in the world are too stupid to be called intelligent. Now, is that a problem? Do you need an intelligent robot if it's vacuuming your carpet? Well, of course not. It doesn't have to be particularly intelligent. But it's surprising how quickly, when you go beyond vacuuming the carpet, you need some intelligence. Imagine, for instance, as is actually happening, that you're vacuuming cleaning robot is also keeping an eye on the house. It's doubling as a kind of security bot. And robots like that are beginning to appear on the market. Now, that robot has to be a little bit smarter than just a vacuuming robot. What if it says that you have a burglar and you don't really have a burglar, for instance? But the one that worries me a lot is the weaponization of unintelligent robots. This is a robot with a gun.
The Army has its own weaponized robot, the Sword's Talon. It's much smaller than the Gladiator. Top speed is 5.2 miles per hour, about the same speed as a running soldier.
If you walk into an ambush site, I'd prefer to have the robot go up first.
Just a short clip. Okay, that robot with a gun was operated by a human soldier. It was teleoperated. The word we use is teleoperated. So is that anything to worry about? Teleoperated robot gun? Well, maybe it is. What if the machinery of teleoperation, for instance, goes wrong, as has actually happened? But that's not really the problem that I'm worried about. I'm worried about the trend toward taking the man out of the loop, the soldier out of the loop. And this is particularly worrying, and I'm sorry if this is getting political, but well, I'm not sorry, because I think these are genuine concerns. This is a drone. We see drones a lot in the news, and something that's happening right now in military robotics is a process that's rather curiously called going from man in the loop to man on the loop. So it's just a one-letter change, but it's rather serious in my view. The idea is that right now, a drone like this, the kind of drone that's currently being used in Afghanistan, for instance, is remotely controlled by someone thousands of miles away, and they're in the loop. In other words, it's that person, that operator, who decides when to fire the weapon, when to fire the drone's weapon. What is happening is that the move that is beginning to be spoken about is to man on the loop. What that means is that the operator no longer flies a single drone. In fact, actually, technically, there are several people flying one drone, but the operator flies a whole squadron. The robots, the drones, act autonomously. They actually decide when to fire the weapon and where to fire the weapon autonomously. The idea of the man on the loop is that this is a kind of supervisor. This is an individual who intervenes if they think that the robot is getting it wrong, is making a mistake. Now, there are clearly ethical issues with that, but I want to draw your attention to the technical problem. The technical problem is this. We simply cannot build the artificial intelligence that will be able to reliably differentiate between combatant and non-combatant, between friend and foe. That technology simply does not exist. The problem is that the expectation of robotics from the movies is kind of leaking into real life. And I'm serious about this. I'm not just saying that for dramatic effect. The problem is that robots like this are being commissioned because the stakeholders want to believe that the technology is possible, whether it really is or not. But no roboticist I've spoken to claims that the technology, the image processing technology, the artificial intelligence technology has yet been developed that can reliably make those decisions. None. So that's my ethical problem number one, the problem of the ethical use of unintelligent robots, dumb robots. My ethical problem number two is that of robots that induce an emotional response. Now, I'm going to now show you a robot and a movie of one of our students from 3 or 4 years ago, called Dave McGoran. This is Heart Robot. Now, Heart Robot was a really great public engagement project designed to look at the potential, the idea of emotional interaction with a robot, particularly an incredibly minimalist, very simple robot. Let me start the movie. This is Dave McGoran.
The Heart Robot is, in some ways, a very obvious way of communicating this world of emotional social robotics. But the future may not necessarily be little humanoid robots walking around that are expressing emotions and interacting with us in an emotional and socially clever way. It may be other objects around us. You know, it may be our laptop that understands that we're getting really frustrated at it and goes, oh, okay, I won't just keep repeating this error message to you. You know, it could be our mobile phone that knows that we're really upset and at a funeral and won't interrupt us with a call. Emotional and social intelligence could appear in many different ways in society, and this as well raises interesting questions. Does it make our world a much more emotionally sophisticated place when we're actually able to relate to our artifacts the way we relate to one another? Or does it make us value emotion?
I'm going to stop there. Oh. And just pause that for a second. So there is the question that I want you to think about of a simple robot that makes us feel something. So the point is this: robots can do that. Not just robots in the movies, but robots that we can build right now. Robots can make us feel. Here's another one. This is a Japanese robot baby seal called Paro. Oh, sorry. Cute. Now, I worry about robots like that not because the robot is smart, but because we, humans, have this extraordinary propensity to anthropomorphize. You know, we do it in our sleep. We can't help doing it. So, however simple the robot, we imbue qualities, characteristics into the robot. We project those characteristics that are not there. Now, okay, that's fine. Is that a problem? Well, I think it's a problem when those robots are being promoted. In this case, I'm not sure if it's a real picture of an elderly person with dementia, but these robots are being promoted as kind of comforter robots for elderly people with dementia. Now, What worries me about that is the problem of an emotional dependency in the human for the robot. You may think, well, that's not a problem. We have pets, and humans have emotional dependencies on pets. It's just like a robot pet. Well, okay, that may well be true, but the problem is that this is an artificial animal. It's not a real animal, it's an artificial animal, and I'm concerned about the deception. I think it's perfectly okay for, if you like, consenting adults or teenagers to be deceived by interesting robots, fun robots. But I'm worried about the ethical issue of vulnerable people, young children, elderly people, for whom perhaps they're not able to discriminate between person and robot. I think that the ethical issue is one of a human vulnerability that I believe could be exploited by roboticists and particularly perhaps by unscrupulous manufacturers. Robots that make us feel. The third ethical problem that I worry about is robots that appear to be intelligent that are not. And again, I kind of wanted to highlight something here that arcs right back to the beginning, to the fantasy robots, the robots from the movies. We're perfectly used to the idea from watching the movies that robots that look like humans or humanoids and behave like humans and humanoids. Here's one, in fact, that we have in our lab, built by a famous robot builder in the US called David Hanson, quite remarkable robot builder. Again, it's worth Googling David Hanson's website. This is a robot called Eva that can emulate human facial expressions. You can look Eva in the eye, smile at Eva, and it will smile back. Of course, when Eva looks sad or depressed or angry, Eva is not sad or depressed or angry. The robot gives the appearance of having feelings. Again, what's wrong with that? It's kind of interesting. But I would say the same thing that I said in the previous example. Robots that appear to have, in this case, kind of social or emotional intelligence that actually do not really have social or emotional intelligence, in fact, any intelligence at all, are a potential ethical concern. The final example I want to show you is a Japanese robot called Actroid.
Humanoid robot, Actroid. Oh, are you surprised that I'm a robot? Take a look at me. I look just like a human, don't I? Well, it is really hard to recreate a robot which looks just like a real human. More than you would imagine. Because you can tell that I'm not a real human if there is the slightest trace of unnaturalness in my behavior or actions. Here is the secret to why I look just like a real human.
Yes, wouldn't we like to know what the secret of why Actroid looks like a real human? This is something that worries me a lot. It's what I call the brain-body mismatch problem. The problem is basically this: we can build the bodies. As you saw there, we can build quite remarkable bodies. Look at the Geminoid DK robot head modeled on a Danish lecturer Henrik Schäfer. That's a robot. That's not, that's not a photograph of Henrik Schäfer. The problem is that that Actroid robot that you just saw in the movie clip is not smart enough to even be on the vertebrate scale of intelligence. The mismatch, the gap between the expectation, quite reasonably, of the body and the appearance and the gestures is enormously different to the reality of the intelligence that we can build. The problem is that to build human-level artificial intelligence that would be an appropriate match to the robot body that you've just seen is probably several hundred years into the future, if not longer. This is not something that can be achieved in the next 10, 20, 30 years, despite what the singularity people say. It's nonsense. So again, I think this is a worry. I'm not sure, and I'd love to debate this with you, I'm not sure if it's ethical to even build robots like this because of this profound mismatch between body and brain. I want to sum up now. Again, these are just preliminary thoughts. What I've shown you, I hope, is that we have a cultural expectation of what robots are and what they do. Heavily influenced by science fiction and the movies, that's fine, that's perfectly okay. But it means that we have, many people have a seriously incorrect expectation. So I think that roboticists have a duty, we roboticists have a duty to not only explain the reality of robotics, which I hope you agree with me is pretty exciting anyway, but to appreciate the problem. I think that, in talking to some roboticists, I'm not sure that they necessarily even see there's a problem. I think there is a problem. I think that roboticists, we roboticists, should not build robots that misrepresent themselves. What I mean by that is robots that have this enormous gap between appearance and actual function, even unwittingly. I think we need to be very aware of that. And finally, this rather cryptic comment about roboticists should resist the pressure to overpromise. I should explain that I, like quite a number of academics in the room, spend a significant proportion of my time writing grant applications. In fact, if we don't write grant applications and bring money in, we stop work. It's as simple as that. But all of the, if you like, the kind of milieu that I've described, the cultural expectation, understanding, misunderstanding of robotics that is shared by everybody, including funders, funding bodies, governments, stakeholders, and so on, together with the intense competition for research grant funding, means that there is a trend, a tendency to overpromise. I read many grant applications as a reviewer, and I'm shocked by the number of grant applications that promise quite extraordinary and impossible things. But the danger is that that's what you have to do to get the money. Now, it's a slippery slope, and if I were able to have such influence, which I don't, I'd, in an ideal world, like to call a kind of amnesty on roboticists who write grant applications, so that we basically bring ourselves back down to earth and only, therefore, promise technologies and robots that we can actually deliver. Thank you very much for listening. I'm very happy to answer questions. And sorry, Paul, I mustn't forget, critically important to acknowledge my wonderful colleagues in the Bristol Robotics Lab. Thank you.